everyone. I'm Jedd. I'm a software engineer at Speckle, and I'm going to do a quick talk about data navigation mastery with the Speckle SDK. So we're going to look at some tricks and tools that we've been building in our C# and Python SDKs to provide some help with consuming Speckle data within the context of an automate function or a Speckle connector or some custom scripts that you guys might be running. And first, let's talk about what do I mean by consuming Speckle data. Well, we often receive and use Speckle data, and we want to extract some information or transform our data. And so the way that we consume that depends on kind of the features that we're trying to implement in our automate functions or our connectors. So before we dive too deep in, I just wanted to formalize some ideas about what Speckle data looks like and hopefully demystify some graph theory terms. I won't go into too much detail, but the data in Speckle is made up of objects and relationships. The objects are our data transfer objects, our meshes, walls, columns, beams, etc. And the relationships are the references between the objects. They're directed relationships, so they're one-way references by ID, and as a graph, the objects are acyclic, so we never have any circular references between objects. So what this leaves us with is some of these graph structures where parent objects reference their children, often in these tree-like structures, not always pure trees. Often we have objects that are referenced by multiple objects like render materials and instance definitions. And what we want to understand is how can we extract and transform these graphs into our functions. So when we look at consuming a graph of Speckle data, we need to know a way that we can select and process these objects. And often that requires traversing this graph. And traversal is just the navigation of the relationships within the graph. The simplest form of traversal that most, I think, people working with the Speckle graph is familiar with is a depth-first flattening of the graph down to some Speckle, a flat list of Speckle objects. And we'll look at some examples first of how we use that and the use cases that this works great for. So this might be found something in like an automate function or a connector or a custom app, but we want to transform the data on the left into the data on the right by adding some colors to our geometry, calculating the color based on the volume property of the meshes, for instance, right? And we can take the data on the left and flatten that down into a flat list of objects. We can iterate through them one by one, asking the question, is this geometry that we want to add a color to? If it is, then we can apply our action. We can create a new render material and set that. And then we can repeat this iteration for each object in the graph. And what we're left with is the output on the right. And the SDKs provide a convenient extension function to flatten the data down. So here we get our Speckle data. We can flatten it using this flatten function, iterate through each object one at a time. And inside the body of the loop, we have our functionality to apply our materials, etc. And here, flat data is really perfect because we don't care about any of the existing relationships between objects. All we care about is transforming the individual meshes. So flat data works great for that. Let's look at some other cases where we're transforming more than just individual objects. We're transforming maybe the structure of the graph or the relationships between objects. And what we'll find is that simple flattening is not always enough. We need the hierarchical context of where an object is in the graph, because that holds some semantic information that just isn't captured by flat data. So the simplest way I can illustrate this problem is with a function that we want to filter out some objects from inside the tree, right? We might do this in an automate function or in a custom function. I don't think we're doing this in any connector, but maybe we are. But this translates to other cases where we want to modify any sort of relationships within our Speckle data. And in this case, we want to remove geometry A, but keep geometry C in our output. If we try and employ the same approach as before, where we flatten the data down and iterated through each object, we're going to run into a slight problem when we try and restructure the data, in that geometry A doesn't know which objects reference it, right? Remembering that relationships in Speckle are directed. A parent references its children, but not the other way around. So we just have flat data at this point. We have no context for where geometry A sits within the graph structure. And so we need some tooling, right, to be able to capture that path that we took while traversing, to keep track of that path for each of the objects. And we can then use that to walk back up the path to navigate with context of where an object sits within the graph. And so this is what we refer to as structured graph traversal, which is a fancy word for just the navigation of objects while capturing hierarchical context. So before we had this flattened function looping through each object. Using our graph traversal functions, the code looks very similar. Instead of iterating through the base objects directly, we're using traversal contexts, which are these wrappers around the base object. So we're still consuming objects one by one, but these traversal contexts also give us their parent traversal context. So we're building effectively an inverted tree as we're traversing. And what that allows us to do is walk back up to figure out an object's parent, object's parent's parent, etc. And before we look too closely at how those functions work under the hood, there's a second problem that I think we want to solve with our SDK tooling with Traversal, and that's we don't always want to traverse everything. We want to be selective sometimes about which properties, which members of our Speckle objects should be traversed. And a wall, for example, has this baseline property to define its start and end point, and its display value to show its mesh-based geometry, right? But take the baseline, for instance, that's just data, right? It's kind of meaningless to use that line on its own without the knowledge that it's part of a wall. So ideally, we want to ignore the baseline property here and the display value properties here and just consume the wall and door objects, right? These are sort of our, in connectors, we would call these convertible objects. And so as part of our requirements or the features of our SDK tooling, we need to be selective and have control over which properties of objects get traversed and which we ignore. So the tooling we've created for both these requirements, and what you saw us use a minute ago, was this graph traversal class. So it consolidates both the structured traversal and the selective traversal features. And the graph traversal class allows us to define a set of rules for which members traverse for which objects. So the traversal rule builder allows us to really easily define these rules. We can specify a function for which objects the rule applies to, and if that rule does apply, then which members of that object should be continued to be traversed. So we can build up these several rules that the function should use, and as we encounter the objects traversing in a depth-first manner, we check each rule one by one, and the first to evaluate true, we then use to figure out which properties to continue traversing, right? And the function you see right on screen right now is a very simplified version of the actual function that we're using in almost every connector, right? Where we only traverse the elements property for convertible geometry, and for everything else, we traverse absolutely everything, right? So that traverse everything rule always holds true. And if you want to learn more about Traversal, our docs are the best resource for that. So how you can define your own rules, why you might want to do that. There's going to be some crazy edge cases or crazy functions that you guys might be writing where you need to create your own rules. But most people are going to be quite happy using the default traversal functions that we provide that kind of mimic the behavior you see on screen right now. Yeah, I didn't want to go too far into the code for this. So if there's any questions, I'm happy to answer. But that is it for my talk otherwise. So thank you all.